Thank you. Good morning. How many of you have read a scientific paper in the last month? Okay, for a number of you, that's probably why you are here. It turns out that we're churning ever more scientific papers. I'll show figures later on. And for this reason, we're conducting studies on them, so seeing how they accumulate. Some types of studies that you see here, systematic studies, so a study on previous science that can be reproduced and done in a specific objective way, not just picking out a few papers from a pile. Scientometric or bibliometric studies where we measure things such as the scientist's output or work done in a specific field. Meta-analysis where we use statistical techniques from existing studies, say how cancer is related to smoking, in order to get better results, and other secondary studies. And as you see here, such studies have been rising from 1970s onward at an exponential rate. Look at the scale on the left, it's a logarithmic scale, something that we will see many times in this presentation. Now they have reached tens of thousands of studies every year. We've been conducting such studies also in our group, such as looking how various data papers, open data papers, are being used by others, or how software engineering research, thousands of papers that are published on software engineering every year, are actually used in practice. And lately, also looking at how machine learning is associated and used in software engineering. There have been so many papers in this area that we conducted what is called a tertiary study. So we didn't look at all those thousands of papers, but we looked at papers that summarized those studies, a few dozens of papers. Research on using existing publication data and building on it demands quantitative data. And two scientists are famous for working and establishing the field. The one you see on the left is Eugene Garfield, a linguist and businessman. He established the Institute for Scientific Information, which became then the Science Citation Index, then was bought by Thomson Reuters, and now it's a firm called Clarivate. And on the right, another famous scientist, Derek de Sola Price, who also worked in this field, established disciplines together with the Garfield of scientometrics and bibliometrics. We can use and measure scientific output and study it using a variety of services, such as the ones you see here. How many of you have used any of those in the past month, say? Wow, a fair number. However, there are problems associated with them. First of all, there's a lack of transparency, repeatability, and reproducibility. A query that you give today on, say, Google Scholar may well give completely different results in a year, and we have no idea how the results appear here, why the results appear in a specific order. Latency can be high, and the bandwidth can be low if you want to run a query on tens of thousands or millions of publications. Good luck going back and forth on an API. And if this wasn't bad enough, there are also rate limits. I have the privilege of having been kicked out of various digital libraries for 20 years, 25 years now. There are also the query languages that we use are also proprietary, so each service has its own query language, and they can be restricted in what you can do. Maybe you can add terms, but you cannot order them, or you cannot search in specific fields. The coverage may be limited. Some services contain only a subset of what we want to search. And finally, there's the issue of availability and costs. Some are lucky enough to have subscriptions to some of these services. Others don't, and even if you have a subscription, getting access to the full data set may be difficult. Thankfully, two developments are changing the status quo. The one is the rise in computing power that we have in our hands. I don't know if you have seen this picture. Somebody delivering, a group of people delivering an Elliott computer to the Norwich City Council, and a few decades later somebody photographing a Raspberry Pi Zero in front of the same building. I've compared the two machines. Interestingly, both are European endeavors, and there are 3 to 6 orders of magnitude increases in power So things that we could do in 56 compared to now are 1,000 to 1,000,000 times better than they are today. So obviously we can use this power. Remember, scientometrics was established on those past decades, to do a lot more. The second development is the open availability of data sets. We are here celebrating openness in software and data and hardware. And a large number of data sets associated with research have now become available, such as Crossref, researcher IDs, United States patents, PubMed, Research Organization Registry. I'll go over them. So, alluding with some lack of modesty, I admit, to the famous Library of Alexandria, how it should be in the 3rd millennium. I've developed a system called Alexandria3k that allows us to perform publication metadata analytics on our desktop. What it does, it provides us relational access to about 2 terabytes of data without needing to have actually this amount of space on your computer, who has 2 terabytes available on their laptop. Exactly. So you don't need it with Alexandria3k. It gives us access to about 4 billion records, 74 tables. You install it as a single Python model. You don't need to maintain a graph database or a cluster to install and maintain. I know it's not a problem for you, but it is a problem for people who are not in computing. And it's also super efficient, so if you run a sample query on the whole data set, but sample it, it can finish in minutes. If you build slices of the data to study, it can finish in between 5 hours and a couple of days, but then you can run queries that finish in seconds. And the space requirements start at about 160 gigabytes for the downloaded data. You can then process it in compressed form without requiring to decompress it. What I will show in the next about half an hour is the model that you get access to and the type of data that you can use. I will explain how it can be used in practice, go deep into how it is implemented, giving you perhaps ideas how you can do similar things, and finish with some issues, limitations, and how to move forward. So what you see here is the schema of all 75 tables. They are colored based on the data set they come from. So on the top you see the United States patent. The various yellow ones are Crossref, is the main data set, contains details about publications and their authors. There's also a similar set from PubMed regarding health sciences, information about researchers, open access journals, research organizations, and some other stuff I will explain. As I said, the main data set is Crossref. You see it here. It contains mainly works, and then these contain references to their authors, the updates, subjects, funders, licenses, and also the affiliations of the authors and the references in each work. In numbers, these are on top thousands, so you get about 135 millions of publications. Not all of them contain or a subject or references, but you see these numbers diminishing, but they have been going up over the years. About 360,000 million authors and about 1.7 billion references. So each work has a reference at the end. You get that many references. Many of the works are also associated with subjects telling us in what area they appear in. Most of the works are journal articles, then come book chapters, proceedings, and other elements such as books and posted entries and dissertations, far, far, far smaller. If we look at the publications that appear in the dataset each year, all these charts, by the way, have been derived through Alexandria3k, you see that they've been increasing at a very large rate over the years. If you think it's exponential, you're indeed right. If we plot it on a logarithmic scale, you see a linear rise, which means an exponential rise in the numbers. You can even see 2 dips in the rise. Any idea why these are there? What happened? Wars, exactly. The wars, apart from the extreme human tragedy, also affected science, the 2 world wars. Regarding availability, These are the various lines show which works have an abstract, a subject, a funder, a researcher identifier, awards associated with the works. And you see that these numbers have been rising in most areas. The subject is a special case. Another data set associated with Alexandria3k is the Open Researcher and Contributor ID. How many of you have such an identifier? Good. If you don't have one, go and get one. If you publish, it helps us, all scientists, associate you with what you have been publishing. And these have some basic details about the persons, and then further details associated with distinctions, education, invited positions, memberships, peer reviews conducted, and other resources associated with researchers who have access to a specific large telescope, for example. Again, the completeness of this data is not uniform, so most people have associated works with them, but fewer have associated employment, education, personal data. A similar data set to the works is the data set of publications published, made available through PubMed, United States government effort, which has publications associated with health sciences, so health and biomedicine. It's similar to Crossref, but it also contains some more specialized fields, such as pathogens, or a very complete taxonomy of where something belongs, or chemical substances mentioned in a specific paper. So it allows you to do more concentrated and specific research. Also available are the United States patents for over the past 20 years, containing about 5 million records, and a registry containing about 600,000 records of research organizations. So the organization you are associated with, if it conducts research, it should appear there, and it's a taxonomy, so it contains the parent organization of your organization, in many cases up to the top, maybe the government. What else is there? Some smaller data sets, journal names, so that you can directly associate them with their ISSN, funder names, and also directory of open access journal metadata, about 19,000 records. All these are tied together through identifiers such as the digital object identifiers, DOIs, the researcher identifiers, ISSNs, URLs, and many other identifiers. In a way you see here, these are just some representative tables from diverse data sets linked together. So how are we using Alexandria3k in practice? You can use it as a command line tool with a typical nowadays for large tools pattern of running A3k, the A3k command, and then a sub-command such as populate or process or query. And here's an example of that. I'm running the A3k command, asking it to populate a database called COVID.tb from the Crossref dataset found in this directory, and selecting only the rows that have a title or an abstract that matches COVID. I will show you later on how this can be useful. You can also use it through Python. Here's an example. You import it. You create an instance for the specific data source that you are interested in, and then you give a similar, you call a method that performs a similar function. Typically, the way to use A3k is to download the data. For Crossref, it's about 160 gigabytes. It can be downloaded through a torrent in about 3 hours. By the way, this gives you plausible deniability argument of why you are using torrent. You can then run various exploratory data analytics queries directly on the sample. This can finish in about 2 minutes for 1% of the records. No need to uncompress this to the terabytes required. Or you can populate a database, a SQLite database. This can take for 4 to 20 hours. The database can be some 4 to 200 gigabytes in size, depending on what you store in it, if you are selective. And there on the database you can test, define, refine analysis queries. The queries can run in minutes or in hours if they are very complicated. Mainly how you can use it, you can run ad hoc SQL queries directly on the compressed data. You can populate SQLite databases, and there you can select elements either horizontally, so you can say I want only the records that match this specific condition, works published in the last 2 years, or vertically specific columns. I'm not interested in the abstract, for instance, because it takes up a lot of space and I'm not going to use it. And then once you index the SQLite database, you can have many queries finish in seconds or even on the complete data set. Here is an example of a query directly on the data set, so without creating an intermediate database, measuring how many publications appear each year, the chart I showed you earlier. Here is another example of a query that performs sampling. It calls a random function of Python, and which returns true when it's less than 0.01, so I get 1% sample from the data set to find out how many works contain abstracts and how many don't. This is the answer, and this runs on the complete data set, but sampling it in about 2 minutes. Another example here of populating a database in order to extract metrics that I showed you previously, how many works have authors or subjects or abstracts associated with them. Similarly, another population completing the ORCID dataset, showing how many elements are there and the corresponding query on that dataset. Let's see some more advanced elements. Here there are 2 papers, both written by Nobel Prize-winning authors. On the left is one by Kohn and Sham, a Nobel-winning paper used to establish theorems to develop a method for calculating the structure of electrons. And on the right, another famous paper, you're probably aware of it, by Watson and Crick, also Nobel winners, introducing a model of the structure of the DNA. However, the way these papers are associated with science turns out to be very different. If we look at the papers that cite them, so the red papers here, the 2 blue ones are this one and this one, we see that for the left, papers that cite the electron paper also cite previous work, so works cited by this, whereas papers that cite the DNA paper do not cite the work published before it. So people have said that the paper on the left consolidates existing research and advances it, whereas the paper on the right, the DNA paper, is a disruptive paper that it changes all things, and therefore people no longer cite other works. They cite only this paper and ones that follow it. There's a measure that you can calculate here. The paper that first established it, published in Nature, gave these numbers here. My own calculation on Alexandria3k gives similar numbers and a very highly significant statistical measure showing that these methods are equivalent. The one on the top, the published one, is opaque. You cannot reproduce it because the data is not openly available. The one on the bottom can be run on your laptop. Here are some other measures, the evolution of scientific publishing after the Second World War. Before that, things were completely different. That's why I'm not looking at it. And we see many interesting changes. Number of authors per work risen from 1.5 to 4. Works per author from 1.99 fell to 1.59. References rose from 13 to 46. Pages doubled to 12. The consolidation disruption index fell. So if you think that science is becoming less disruptive these days, it is true. Number of citations, works published, journals, works cited at least once, and impact factors have all risen exponentially. All these calculated with queries you can find on the software you can download from GitHub. Here's another interesting chart showing how the evolution of publications has changed in specific fields. You can see the big rise in computer science, the purple thing that has increased substantially over the years, and also the relative fall in publications in arts and humanities, the other purple here, that has diminished in this way. The absolute number has risen, don't be fooled, because publications have risen exponentially, but still it occupies a lot less than it did in 1945. Here are examples of 2 other data sets. Here is the evolution of applicants by year and country of US patents. You see a fall in the number of patents associated with the United States and Japan, and the rise from a low base of patents associated with China on the bottom, the blue line. Another one associated with replicating a paper looking at specific software, statistical software used in health science public research. And again, you see with green the original paper, and with orange replicated results with Alexandria3k. This was completed by a TU Delft student in a couple of weeks. Let me show you a more substantial example of what can be done with Alexandria3k, a proof of principle of concept study on a specific topic, namely COVID-19. What you are seeing this was while checking the data set. Is a publication I found in the American Journal of Ethics, COVID Care in Color, which was published by an author, a nurse working in a Bronx emergency room team for 6 years and painting for 25 years. She captioned it as "Fear of an unknown contagion is dreadful, especially without proper protective equipment." So at the beginning of the pandemic, when we were conflicting information on how and when to use our PPE, we relied on each other. I created the data set in the way you see here. I populated a vertical and horizontal slice in an SQLite database, selecting some elements with those that matched COVID in their title or abstract in around 9 hours, about 3 gigabytes of data, and then once I indexed it, it rose to 3.6 gigabytes. And we can see some numbers: 500,000 of published articles, 2.6 million authors. Imagine the amount of effort that went into there, and 8 million references. I'll go more there. What are the topics associated with this research? Everything you can imagine. You can see education and engineering featuring very high, of course, after general medicine, but even strategy, management, law, cultural studies, pollution, anthropology, AI, waste management, ocean engineering, all over the place. Who funded that research? This is the query I ran. National Natural Science Foundation of China, the highest number of publications, and then National Institutes of Health and National Science Foundation from the United States, followed by various trusts and councils. However, if we look at the affiliations associated with COVID publications, these are the queries that established this. We see that first came the government of the US, then the University of California system, University of Toronto, and so on. Here I used the research organization registry, and I moved the organizations up to the parent organization. So Berkeley, for instance, and University of Southern California rose, and UCSD rose to the University of California systems. Another question is how quickly could we look and work on each other? So how scientists publishing COVID research could cite each other. Was it taking too long a time because things were advancing too fast? And what I have plotted here is publications citing other COVID publications published each month. And you see that fairly quickly, even on April 2020, there were thousands of citations to other COVID publications, which rose to hundreds of thousands late in 2020, early 2021. The number you see at the beginning is an artifact, journals that got published with a January date, although they appeared a lot later. This shows us we shouldn't blindly trust our data. I also looked at collaboration. I found some amazing things. There were articles with thousands of authors, authored by thousands of people. So you see articles by 2,000 or 1,700 authors. I thought this cannot be true, so I looked at it and I saw that there were indeed, most articles had a number of, say, 5 authors, but there were articles with 7,000 authors. I looked, I couldn't believe my eyes, I haven't seen such thing before, and it was indeed published here. The number of authors appear in a footnote, pages 20 to 28. And this is not an isolated case. Through other queries, I found many articles with thousands of authors, showing a way of collaborating in an amazing way. People probably contributed by giving data from hundreds or thousands of hospitals, and all these were collected on papers. Let me switch subject. How many of you heard the impact factor? Yeah. What is the impact factor for those who haven't? It's a measure that tries to see how important a journal is by measuring the citations articles in this venue appear in a given year, divided by the publications in the previous 2 years. It has been severely criticized, especially when it's used for measuring scientific worthiness or productivity of authors. But another problem is that it is opaque. So Clarivate publishes, but we have no idea how exactly it derives those numbers. It publishes the method, but we cannot replicate it. We can with Alexandria3k, with queries and populations such as the ones you see here. And we can get results that rank journals by impact factor with a very high significance correlation with the ones published by Clarivate. And through this, we can do queries such as find the most cited article in the last 2 years. And it is this article establishing a method where you can find how matter depends, so the properties of steel, based just on facts associated with the atomic structure of that. I found that very strange, a very specialized subject. So I ran a query to find what publications are citing this article. And I got results, the titles such as these, at a rate of about 8 records per second over the entire data set. If you cannot understand the titles, this is how people outside computing view us when we talk shop. I also looked at cited articles over the last 2 years, but published in that period. And predictably, this was clinical features of patients infected with the 2019 novel coronavirus in Wuhan, China, the first article reporting on COVID-19. Another metric of author productivity is the so-called H5 index, so how many papers you have published in the past 5 years that have been cited at least that number of times. I found an author that has an index of 76, which amounts to 15 papers a year, and many authors having more than 60 papers, an H index more than 60 and 100 more than 38. This was too large to believe because it's not only what was established previously, hyper-productive authors that publish papers one paper every 5 days, but also papers that got cited a lot. So how could this happen? Using again A3k, I looked at papers that were cited, the papers that those authors cited, and looked at those graphs. And what I found is that those papers were cited a lot more between them than papers of other authors with a high productivity, but not that high. So this seems to suggest that some sort of click is working there, authors citing each other and thereby elevating artificially their H5 index. Whatever number you use, you can game it as you can understand. Finally, here's another interesting chart. Here I'm looking at what topics cite other topics. And for instance, we can see these are the 50 strongest relationships, and we can see, for instance, that cancer research cites a lot chemistry, organic and inorganic chemistry. I will finish with some details regarding the implementation of Alexandria3k. I hope that you will get a few tricks that you can use here. A3k is based on a plugin architecture. So on the top you get the command line interface, which uses the Python API, which you can also use directly. And below it there are 2 sets of plugins. Data sources, the various I showed you. You can create new ones by creating a file that establishes a new data source, say archive publications. And processes, things that manipulate data in new ways. For example, matching authors with their affiliations or disambiguating authors with their same name based on what they publish. And finally, at the bottom is the plugin API that these plugins use in order to function. The main ideas behind the Crossref implementation and the other databases is SQLite and virtual tables. Virtual tables are a feature of SQLite that's magical. You can create tables that don't exist as real in a real database, but appear as tables which you can access with the select and other SQL statements. It uses a method to partition the data because large databases come in many, many files, tens of thousands of files for the case of Crossref. I use the number of each file as an index so that the database, the virtual table implementation of SQLite does not jump from one partition to the next because decompressing partitions is expensive. Another trick is to understand, once you have written a query or a selection of what data you are interested in, how to understand what tables or what fields you want from each table. I don't want to parse SQL, and especially with all the specific implementation details and of the SQLite. So what I'm doing is I ask SQLite to trace the analysis of the query, and thereby I can understand which columns and tables it touches. I also create vertical slices of the partitions for the queries in order to run faster, and I use various queries to only look within a partition in order to populate records. So the Crossref data appears in JSON format, and in a self-contained file, one of the 26,000 files, it will contain all references to each work. I don't need to go to other partitions. So here's an example. When you run the query on the top, what is happening underneath? A virtual table is created, and the query is run on this table. Fairly simple. When, however, you also do joins, what is happening is it is creating the tables, but as you see here, the tables have a container ID restricted to each container in turn, 1, 2, 3, up to 26,000, so that each partition is decompressed in turn and not all of them are run together. And then this is run on tables that are actually realized. For population, similar things are happening. So if you populate something with a condition, so I want only those subjects associated with library information sciences, and you want only some columns. First of all, tracing establishes the table name and the field that you are interested in. And then again, on partitions, tables are populated, and then queries are run to fill the data that you want from the populated tables. I found that this is faster than using virtual tables because of the various joins. A thing called topological sort is used to establish in which order the joins have happened based on the names of the tables that you want to join. Similar ideas for populating ORCID, United States patterns, and so on. Here, because these appear as XML records, we can skip the parsing of XML records that we are not interested in, and thereby gain an additional efficiency advantage. Let me finish with some issues and limitations of A3k. The coverage of authors is fairly low, so about 17 out of 360 million authors have an associated ORCID with them. Keep in mind, data go back to the beginning, to the Second World War, so ORCID wasn't a thing then. But even now, not all authors have an ORCID. This is improving because many institutions ask them to, and we're also investigating ways with which we can disambiguate authors even if they don't have an ORCID through machine learning methods. Also, affiliations, either they are missing or they appear in diverse forms. So the same university, say the one here, can appear as ULB or the full name of the university. Abstracts are also not always available. A small number of them have an abstract, but many publications also have a text mining link that you can use in order to obtain the full text for data mining purposes. The subjects of publications are based on an identifier established by Scopus, which is associated with complete journals. So if something appears in a zoology journal, we assume it has to do with zoology, even if it has to do with, say, biology or bioinformatics. Again, we're working to use machine learning methods in order to obtain better results here. And looking specifically at the impact factor calculation, which many are interested in, establishing what is a citable item is tricky. Clarivate uses a proprietary method where, for instance, an editorial or a letter is not considered citable. It's difficult to do this automatically. I assume they have people working on that. Way forward and how we can work as a community to improve A3k. First of all, these are the early days, so I'd be very happy to help the community conduct studies. If you have an idea for something, for a way to use A3k, please contact me. I would like to integrate more open access data, so here are some ideas. Archive, the DBLP, this is a database of computer science papers. There is a taxonomy of medical research called MESH, which is extremely interesting, and a wider one used by the Public Library of Science that I also think would be worth integrating and associating works with it. Associated with that is improving the various processes, so things in which we can process the data, disambiguate authors. There are many John Smiths or Zhu's in China, find out which are the ones that have written a specific article, and classify the topics of the publications. And finally, and this is relevant to us here at FOSDEM, evangelize more and better data availability, more use of ORCID, and publication improvements on the published metadata. With this, I thank you for your interest and attendance here.
I think we should have time for one or two questions. Do we have questions? There, over there.
Thank you for your talk. So about 10 years ago, I participated in a Kaggle contest which was about disambiguating authors to link papers written by the same authors. In the work you've done, have you observed indeed ambiguity in the different forms?
So sorry, can you repeat? I'm not hearing very well.
Sorry. So I was saying that about 10 years ago, I participated in a Kaggle contest where the topic was finding the different papers written by a same author, because the names had different variations and formats and so on. In your work, do you also observe that the names of the authors are written in different ways, and that makes it harder for you to link papers together?
All right, the question is regarding a contest that was run 10 years ago, whether there are authors that have their names appear in different forms. Absolutely. First names often get abbreviated to the first letter. Middle names appear and disappear in random order. So it's indeed a problem. ORCID helps, but also efforts such as what you did to develop ways in which to establish uniquely an author with all their works are helpful, and they can be integrated as processes, either with a pull request on A3k or by using the API and doing it on your own.
Hey, so it's a two-parter. First, how often do you update the data set? And is there a way to download the delta? Like just get the new stuff?
Okay, two things. How often I update the data set? The answer is never. In contrast, say, to OpenAlex, A3k is a tool for working with existing data. So whenever you want, you go and fetch the data. It is not, it doesn't come with the data. You use the data sources from their primary source. I don't pretend to curate the data. I use A3k allows you to use existing open data sources. Can you work with incremental updates? If you have a way to running a select, if you have incremental parts, you can populate the data also with the increments if you have a database that you populate incrementally.
Thanks. So I was in university 10 years ago, and but more than 10 years ago, and by that time our articles were published mostly as unstructured text. So is that still a thing? Are there any, are you aware of any efforts to make articles structured tests, because they're unstructured tests and those are difficult to analyze?
Mm-hmm. If I understand the question correctly, whether there are efforts to structure the articles in a way that we can better analyze it. There are tools such as Grobit. We heard it yesterday at the dev room on Open Science that do that, and they create XML associated with an article's text. Of course, this cannot always be perfect. Ideally, we would want the complete pipeline from authors to publishers to publication to take this structure into account and not reverse engineer the structure after it has been published.
Well, when I look at the time, we should stop here for Q&A here in this room. Maybe here's some more time. So maybe some applause. Yeah. And FOSDEM wants to say thank you.
Thank you very much.